the state probabilistically collapses into one of the eigenvector states of the observable. And you have lost all previous information about what the state was to begin with. And secondly, when you measure that state again, you keep getting back the same state that you had previously. So like the strong measurement formalism was discussed in the talk, so I'm not going to go over it, but we basically use these projection operators and we use these projection operators M, and we use these to calculate the probability for a particular outcome. But now, like when you take a lot of quantum objects and you try to scale it up into the classical scale, what happens is that now you have a notion of this collective measurement, that when you do that, the state no longer collapses into one of the eigenvectors, and there's like minimal or very little disturbance caused in the actual state of it. And secondly, operators commute. That is, like there's a simultaneous, you can measure several properties simultaneously without there being a contradiction. So this happens at the macroscopic limit. And we discussed these for the quantum objects, and it's very obvious. But there exist correlations that are not quantum. So we have this no-signaling polytope, which has 3 regions defined on it. One is the local region, which has a SH value bounded by 2. One is the quantum region that has a value bounded by 2 square root 2. And then the algebraic maximum value is bounded by 4. And that is the edge of the no-signaling polytope, defined by the PR box correlations. So just as a quick recap, these are the PR box correlations. Alice and Bob each receive an input X in 0, 1 and output a Y in plus minus. And when this condition is satisfied, and these are the probability distribution, this is the probability distribution for it. So what would happen if we now, instead of taking a collection of quantum states, we now look at a collection of PR boxes? But we know that PR boxes are maximally non-local. So what if we introduce some noise in the PR boxes, and then we look at a collection of collective measurement of that ensemble of PR boxes? So what is that relation between the number of boxes and that noise parameter, such that the Sirius bound is recovered? So first of all, there is no like notion of measurement on PR boxes that's well defined right now, which is why we go towards weak measurements, which is a generalization of strong measurements. We take both the system and the measurement device to be quantum systems. So the weak measurement formalism is defined right now for only quantum systems, and we are extending that to PR boxes. So the general weak measurement procedure is that we weakly couple the measurement device and the quantum system. And once that entanglement is done, then we just strongly measure the pointer device, the measurement device, and you get back a value for the position of the pointer. So the pointer function can be normally distributed. And if the standard deviation of that normal distribution is large, then there's a significant overlap. And if the standard deviation is small, then there's a lesser overlap. If you end up measuring your pointer in a region where there's an overlap, then you're not sure whether you measured which eigenvalue you measured. You are in a superposition of the multiple eigenvalues, and you have not collapsed your system into one of those eigenvalues. On the other hand, if you measure your pointer in a region where there is not a significant overlap, like here or here, then you can say that with a high probability your eigenvalue was +1, and with a high probability your eigenvalue was -1. So the weaker you want your measurement to be, the larger you should choose your standard deviation. So technically, we have these. We have the state, and the observable that we want to measure on that state is capital A, and we express the state in the eigenbasis of the observable we want to measure, and this is key for weak measurements. And we entangle that with the pointer function. And this when we do this entanglement, we end up with summation over all possible eigenvalues of your observable, and the integration represents all possible values for the position pointer x. So now when you measure your pointer function, the integral sign goes away and you're left with a superposition of eigenvectors. So to apply weak measurement to PR boxes, we need some sort of quantum language to express the PR boxes. This was proposed by Asen et al. And the procedure is very, very similar to how we normally define the quantum correlations, except that now the operator O, the state O, is a pseudo-quantum state. It ends up giving us negative probabilities. Phi plus and phi minus are projectors on the Bell states, and you have alpha plus minus defined below. And the observables are the regular sigma x, sigma y, and for Alice, and then these for Bob. The key thing over here is that we would need to express our Bell state in the eigenbasis of the measurement being observed, of the measurement choice, basically. So the 4 possible measurement operators for Alice, I explicitly calculated them, and then the 4 possible measurement operators for Bob. These are just like the eigenbasis of these measurement operators. And when I do this, I recover the PR box correlations, so that just, it's a verification process that this construction works. So now if we go on to apply weak measurement, we have the state, we have our pseudo-quantum state, and now in order to weakly measure the state, we need to express that in the eigenbasis of A and B. So the first qubit will be expressed in the A basis, and the second qubit will be expressed in the B basis. And after doing computations, this is the psi plus plus state is the eigenvector for +1 for A naught and B naught. So you have these coefficients that you can look up. So for instance, phi plus in the A naught B naught basis, you just look up the coefficients from the table, and in general you can define phi plus minus like that. And then the combined state of everything is you still take the alpha plus from the initial slide, and you have your state. So this is, we haven't done any measurement yet. We have just defined our pseudo-quantum state in the measurement basis. After we weakly couple our state with our measuring device, we end up with this long expression, which is an integration over all pointer values of x, all pointer values of y, and these coefficients of the, so the psi plus plus is now essentially plus plus. I just didn't write it because it was getting cluttered. Now when you measure this, you end up with one particular x outcome and one particular y outcome, x naught and y naught, and you've collapsed your superposition, the integration, into one long superposition. And this is, you've weakly measured your pointer device. You've strongly measured your pointer device, and you haven't collapsed your function. You still have a superposition of multiple eigenvectors. It is expected, like even if you see this graph over here, if you measure your pointer state in the state 0, you haven't really gained any information, and your state remains the same. So after doing some numerical simulation, I get the same density matrix before measuring it and after measuring it, if I get the pointer position in 0. So now let's take, instead of taking a normal distribution, I take a uniform distribution, and I choose D such that there's no overlap. If there's no overlap, then it's essentially a strong measurement, and I get back the, the only non-zero probabilities are these 4, and these give us back the original PR box correlations. Now, if there is a overlap between your 2 pointer functions, then your outcomes can lie in the left, middle, or the right regions. And now if I perform a measurement, if the outcome is left, so L, LM, and ML, these are like, the first one is for Alice and the second one is for Bob. If both of them measure their state in the -1 position, then your state is minus, in the -1 region, in the left region. But even if there's one L, you know that it's minus for sure. The only case when it does give a superposition is when both Alice and Bob measure it in the middle region. So these are for A0, B0, A0, B1, and A1, B0, and in the last case, you have the middle region. So you have non-zero probability of being in plus minus or the minus plus state. So this is for the perfect PR box. What would happen if I introduce noise in it? These are the future directions I'm looking on. If I introduce noise in it, then I will not have a then my probability distribution would not be just this and this, it would have the other states with some probability in it as well. So the next step to do would be to define noise in this formalism, and then come up with, and then see if the measurement basis that you choose, does it remain the same, or is there some other optimal measurement basis that you can choose? Secondly, this was for one PR box. How do you define these pseudo quantum states for multiple PR boxes? And then you do what I initially discussed. You apply these weak measurements to the ensemble of n noisy PR boxes and somehow relate the number of PR boxes to that noise quantity in the PR box, the epsilon factor. Thank you.